Hello! How's everybody?
Awesome.
Good.
Yeah.
I'm so glad that everybody decided to dress like me today. It was dressed like Mr. Alley Day.
Yeah, it is. I was just going to say that.
Yeah, it's really cool.
Mr. Alley, you need to try it. You're ready.
I know. I'm in the spirit. It's exciting. Today we are continuing our conversation about chemical reactions, and we are going to be writing, balancing, and using chemical reactions. So how do we write out a statement that lets somebody know that a chemical reaction happened? We will go over this again in chemistry in 2 years, but it's good to be exposed to it multiple times. So here you go. A chemical reaction is something that, or a chemical equation, shows what happens in a chemical reaction. So a chemical reaction is what goes on in your beaker. And then when we want to write down what happened, we write this like math statement sort of thing called a chemical equation. And the things that are to the left of the little arrow symbol that we have, we call reactants, because they're the things that are reacting. And then the things to the right of the little arrow symbol, we call products, because that's what we've produced. They're the things that we've made. And then the little arrow sign we read as yields. So you'd have something as reactants, yield something as products. Just like in a math sentence, we would say equals for that little parallel line structure. We say yields for the arrow. Okay? You are still writing. Okay. So this is an example of a chemical reaction here, where we would read that CH4, which is methane gas, plus oxygen, yields water and carbon dioxide. So that's how you would read that statement, right? So the CH4 and the O2 are reactants, and then the little arrow is yields, and then the H2O and CO2 are products. We are combining methane gas with oxygen, which just means we're burning the methane gas. And what we get is water vapor and CO2. Okay, so CH4 plus O2. Now, we need to balance chemical reactions, because if you just look at this, you say, oh, on this side I have 4 hydrogens, but on this side I only have 2. And then if you were to leave it this way, you'd be like, what happened to the other 2 hydrogens? Did they cease to exist? Did they slip into the void? Oh my goodness, what happened to those hydrogens? And so we have to balance a chemical reaction. Right? We've got to see that everything on one side shows up on the other. And similarly, there's 3 oxygens over here, O and O2. There's only 1 oxygen here. So like, oh, I see. Every time I burn natural gas, God creates another oxygen atom. No. We have to balance, right? We have to balance these things and show that they're the same on either side. So what we do is we add coefficients in front of numbers, or coefficients in front of items in the reaction, so that we can get them all to be the same on both sides. So 1 carbon here, 1 carbon there, that works. 4 hydrogens here, H4, but only 2 here, so I've got to put a 2 in front of the hydrogen. So now there's 4 hydrogens. Okay? And then 4 oxygens, 2 times 2, 4 oxygens, 2 times 1, plus 2 more, 4 oxygens. Okay? So this is a balanced equation, and when you're writing equations, you write out the species, the items that are involved, and then you have to say now what's the ratio of this thing to this thing, and how do they go together. And you've got to put the coefficients in front so that it all is the same. Take a second, write that down. Okay, so heat or thermal energy is always a factor in chemical reactions. And when we get to this concept again in chemistry class, we're actually going to spend 4 chapters looking at heat and chemical reactions and how energy flows through reactions. But for right now, this little slide will represent the idea. Sometimes it's written into the reaction equation so that we can see where the heat either enters or leaves the reaction. We want to make sure that we can track the heat where it's important. So sometimes they'll put Q in a reaction. Now, there is no element Q. So if you see symbols of elements and chemicals, and then you see Q, Q is not an element. You're like, wait, what's that? That's quacky symbol. No, what's the element that starts with Q? It's the queasy. No, what is that? It's heat. And I don't know why they use Q for heat. I wish I understood. It probably, yeah, but see, there's elements that have H, hydrogen, right?
HT.
So maybe they just decided to pick something that doesn't exist so that it's easy to understand, but Q doesn't make me think of heat. So you just have to remember that Q is thermal energy. So in this example equation, 2 units of hydrogen gas plus 1 unit of oxygen gas. If you allow them to react together, you burn the hydrogen gas with oxygen, right? Then you get water vapor, 2 units of H2O, and it gives off a lot of heat. So when you're burning hydrogen, it gives off heat, and you get water vapor as the exhaust. This is what happens in the fuel cells of a lot of like Apollo era spacecraft. Modern spacecraft do something a little bit different, but back in the 60s and 70s when we were sending men to the moon, the Apollo program was run on this equation, and they got their drinking water as the exhaust of their engines, which is pretty smart. You burn you burn hydrogen with oxygen, you get heat, you get thermal energy, you can use it to drive an engine, and then the waste product you can treat. So it's kind of cool. But this reaction produces heat, so we put Q here. There are other examples where heat is needed as a reactant to get the reaction to happen, so you might see Q on the other side too. Okay? So there are 4 kinds of reactions. 4 kinds of reactions. The first one is called a synthesis reaction. A plus B gives you A and B. Now, these aren't elements, right? Hey, keep it down in there! Just kidding. So A plus B, those aren't element names. That's just something plus something gives you those things joined together, right? So this is like boy goes to a dance by himself, girl goes to a dance by herself, and then they see each other across the dance floor. Dum, 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 dum. And then they start dancing. Oh, and it's this beautiful thing. And if it's a Disney movie, they're married the next day, right? So A plus B yields AB. Unless it's frozen, because there we finally learned that you can't marry somebody the first day that you meet them. Decomposition reactions are the opposite of a synthesis reaction. That's where there's a pair, there's a couple, but then something happens, and they split up. And you have A by itself and B by itself. Okay, so this is a couple that breaks up over something. So some substance that dissolves or flies apart. Then there's a single replacement reaction, right? Where you have a couple, you have something joined with something else, there's a chemical bond here. And then along comes something else. And the couple breaks up. And A is now with C. And B is by itself. So here this is a couple that goes to a dance. And while they're dancing, the guy looks across the room and there's this cute girl by herself. And he decides to go dance with her. And his date is now alone. So whatever compound this was, it has now been partially replaced with something else. So there's a new compound and something has been kicked out. Okay? So for example, if you were to put, if you had silver nitrate, there's a silver ion and a nitrate ion, and they're a molecule. But then you put copper, metal copper in that liquid. What's going to happen is the copper is going to wind up bound to the nitrate, and the silver is going to be kicked out. And so it's just replacing a pair, replacing something in a pair. Okay? And then double replacement, this is 2 items that change partners. So you have 2 compounds that are mixed together, and part of one compound winds up bonding with part of another compound, and then the leftovers get together too. So this would be two couples go to a dance, and while they're dancing, the couples decide that they would rather be with somebody else's partner, and then they start dancing with somebody else's partner, and they wind up with that person, right? So a quick example of this would be if you take hydrochloric acid, hydrogen and chlorine, and sodium hydroxide, sodium and hydroxide. What winds up happening is the hydrogen and the hydroxide wind up forming water, and the chlorine and the sodium wind up forming salt. So you take an acid and base and you get salt water. And that's just an example of two things that switch parts. This is called a double replacement reaction. Okay? Here's just a quick little fun video that helps us understand this. So you saw this last night? Yeah.